Okay, now let's look at common divisors. We want to find D equals GCD of 1199, E equals GCD negative 2114, F equals, all these GCDs basically are right now. So these are relatively quickly done. I try to use, we don't have to use anything extremely complicated to solve these. You could easily just kind of guess sometimes, especially with these types of numbers like 11 and 99. Yeah, if you know your times tables, you know right away. But in case that it's not, let's do this like if we had like a really large, a somewhat large number. Compare two large numbers. But 11 is prime, so that means 11 and 1 are its only factors. Itself and 1 are the only factors that can make at least positive factors. Yep. But no, basically, like, prime means it can only be divided by negative 1 and 1 and itself. Basically, you can divide by those, and that's it, basically. Negative, basically. Whatever, let's not worry about the actual prime definition, though. The point is that, 99 equals 3 times 33. We basically put into primes. We factor into primes so that it's a product of primes only, and 3 times 3 times 11 is what 99 can be represented as. It's all primes here. And we take the common terms to the lowest power. So 11 and 11. 11 to the 1 power, 11 to the 1 power. Okay. So we have negative 21 and 14. I just put negative 1 out there just to make sure we're clear, but it can be represented as negative 1 times 3 times 7. Technically, we're not going to worry about the 1 though, because 14 is equal to 2 times 7. They have 7 in common, and that works out. So 7 is the GCD, 11 is the GCD up here, 7 to the 1 power, is here. F equals GCD of 14 and 15. I think you can tell it doesn't sound like there's going to be, and there isn't. 2 times 7 is this factor down in the primes, and 3 times 5 is a product of primes. And there's none, so 1. Good. And then you can call this relatively prime. That's what 14 and 15 are. And here's GCD of 1 and 0. It's equal to 1. Yes, I do this to intersection point to show it. Positive divisor of 1 is A equals the set 1 instead of, the set B equals, the B equals set of all positive integers for 0. That's how many, 0 can divide by anything. You can do 0 divided by 1, 0 divided by a million, 0 divided by 554 trillion 300 billion. It'll be 0. But, it's still dividing by something. So 0 divided by anything basically equals 0, but you can do it by anything, so that means we have all the, since we only care about positive divisors, we have all Z plus. So the intersection of these sets is obviously just 1. Okay, now here's another problem. Find, okay, so we have 5 parts, but they're pretty simple, I think. We're just doing several greatest common divisor, and it's supposed to show you a property at the end. Basically if you have all these things, basically find a GCD of 3 numbers, what they'll be, and then all that, I think. Point is, that's not the point, just showing R equals GCD of 1442 is equal to 2 times 7, which is equal to 14. Basically we get that by 1442, we put down 2 times 3 times 7 and 2 times 7. 14, yeah, 2 and 7, 2 and 7. All to the 1 power, so we just take them. Do them. That's GCD though. That GCD here is going to be 7 because 14 and 35 factor down to 2 times 7 and 5 times 7 respectively. And 7 is the only common term, so 7. 3 is T equals GCD of 42 and 35. And the answer is 7 for this one. Because 42 factors down to 2 times 3 times 7, as seen up here as well. And 35 factors is 5 times 7. So we get 7, just a common term. 4, again it's 7. I know this seems repetitive, but yeah, but U equals, these all have letters to them. We could even right here. In 2, it was S equals GCD of R, say 5, but R is found here as 4, R is GCD of 1442, so we just put in 14 there. Basically, that's why I went, but basically now let's go back down to U equals GCD of 14t. T is 7 from here, so it's 1417 GCD. That's 7. 14 is equal to 2 times 7. 7 equal to 1 times 7. So 7 is common. Number 5. GCD of 1442 and 75, yep, also be factored, equals 7. And you can technically do this way. 2 times 7, 2 times 2 times 7, 5 times 7, all it's in common is 7. So, oh yeah, and S equals 7, U equals 7, so, yeah, remember we're trying to state that S equals U equals GCD 1442 75. We're supposed to show that. We're supposed to basically confirm or deny if it is, yes or no. And we just show that by doing this calculation real quick, because we already know S and U are 7. Each 7, and now it is 7. So which integers in the set 1, 2, 3, 4, 5 are relatively prime to 5? This is 5a. I set it up somewhat nice and do, so X is in this set. In definition relatively prime, we want GCD of X and 5 equals 1. Positive divisors of 5 are 1 and 5. X cannot, basically this means that since 5 is prime, we can just say 1 and 5. So it cannot be a multiple of 5, basically. Be relatively prime, it can't be divisible by 5. Basically it can't be a multiple of 5. 1, 2, 3, and 4 are relatively prime to 5. We can tell from that. Now for 5b, which integers in the set 1, 2, 3, 4, 5, 6 are relatively prime to 6? X is in 1 to 6, basically. GCD of X at 6 equals 1, because that's what relatively prime means. And positive divisors of 6, 1, 2, 3, and 6. So 2 cannot, basically 2 does not divide X and 3 does not divide X. So X is in 1 and 5. So 1 and 5 are relatively prime to 6. Basically that's all we're saying. Trying to, basically these factors, things of 6, 2 and 3. And then that's what it means. Of course, we don't have to say it can't be divided by 6, because anything divided by 6 will be divisible by 2 or 3, basically. That's how I look at it, at least. 12. Let 72 equals 99h plus bk with bh and k and z. What are the possibilities for the value of GCD of 99b? Very similar to, there's other ones like this, but they actually don't, they have just a and b instead of 99 and b, where it would be ah plus bk, but for the most part it's the same process. So you basically write out the linear combination 99 and b, or you state that this is a linear combination of 99 and b. No, a linear combination is something equals ah plus bk. Basically, it's just we have a term for a. And we can just state, we state out a lot of stuff we see from this thing. That d divides both of them, implies that they equal d times something, times an integer. And this applies that 72 equals, basically, I plug in for 99 du, and b it's substituted with dv, so it's dvk and duh. And so 72 equals t times this expression, so d divides 72 basically. So what this is kind of stating the points to show it out. The set of positive divisors of 72. Yeah, because 99 divides, yeah, basically was shown. Yeah, set of positive divisors of 72 though. They're all laid out here. We basically make set A of that, a set B of positive divisors of 92 in this case, 1, 3, 9, 11, 33, 99. And then C equals A intersect B, which is 1, 3, 9. Possibilities for GCD of 99B are just 1, 3, and 9. If it was A and B, you could stick with A. You'd only have to do this part, and then that would be a set of possibilities is all of A. But since we have 99 and not just A and B, that can be any number, or any integer, in this case, since we're dealing with a set of integers for all these problems. You know, unless otherwise stated. So basically, yeah, you just have to find that intersection of A and B in this case. Yeah, 72 equals 92, and basically it's just staying something that we also should remember. 99 and B equal, so that, and that's equal to GCD of 99B times D. But the answer is the possibilities. 1, 2, 9. Okay, another problem after this one on. So this one and one more. So prove that square root of 5 is irrational. Yeah, basically we're saying that square root of 5 is not a rational number. It's irrational. So assume square root of 5. We basically do proof by contradiction, which you'd see down here. We assume that square root of 5 is like in Q, which is a set of rational numbers, and we have to show why this creates a contradiction. And when the contradiction is shown, that means that it has to be the opposite case. It cannot be a Q. I mean, that's it. So this implies that it can be, because remember A, B. This is the rules for it. If square root of 5 is rational, it has to follow these rules. It's equal to A divided by B, where A, B are integers, B does not equal 0, and most importantly, which we're going to use is UV is in Z. Not UV. Where did I write it? Yeah, the GCD of A and B here, basically they have to be relatively prime. You have to basically not be able to reduce it anymore, is another way of saying that, but basically relatively prime. That's what A and B will be for a rational number. We say it down here when we do this. So D is equal to GCD of AB. We let that be a case. That means that A equals D times U and B equals D times V. Because it's divisible by D's then. You have something multiplied by D equal A or B, depending on which one it is. UV is in C and V does not equal 0. And what's very important to note here, if we're letting this be the notation, is that GCD of U and V equals 1, and that comes from the fact that you have to have these numbers be relatively prime when the division of A and B basically then has to stay relatively prime. And for that to happen, U and V have to be relatively prime, basically. That's basically the gist of what's going on here. That's not fully said, but is implied by all this. And it's right here. That's why UV has to equal 1 to GCD. So square root of 5 equals du dv, which we substitute in A and B. We substitute du and dv in. D gets eliminated. So U and V are what's left. And these have to be relatively primes then. That's why. That's how we set this up, basically. This implies that U equals square root of 5 times V. So we contradict the fact that they're relatively prime by showing this. So U equals square root of 5 times V. If you square both sides, you get U squared equals 5 times V squared. And that means 5 divides U squared. Now, if basically U squared is U times U, if 5 divides U squared, that means 5 divides U because of that. Because U squared is U times U. And, basically... if the square of a number is divisible by something, then the number itself will be divisible by that number, is basically what's going on here, unsaid. Completely unsaid, just implied from it. From what I understand of it. There's many cases you can just think of it. It sounds like a trend. Like, 5 squared is 25, and that's divisible by 5. But in general, you could also say 10 is divided by 5, divisible, and 10 squared or 100 is also. It just seems like something observable, and it's probably very easily, provable if we really wanted to go down a path, but we don't have to. But U equals 5 times M, we let happen now. Yeah, because we know that from 5 divides U, U equals 5 times a number. That's one of the most, that division thing is very important to understand how divisors work like that. Especially for any exam that would focus on a couple of these ideas I've been talking about these last few sections. But 5m, this means that 5m squared, because U squared equals 5 times V squared, 5m squared equals 5 times V squared, which means that 25m squared equals 5V squared. It's through simplification. And that means further that 5m squared equals 5V squared. which implies that 5 divides v squared, which implies that 5 divides v. Like before, you can understand that last step. But no, basically 5m squared equals v squared because you divide by 5 both sides. Then, but it works out because, yeah, because 5m, because it's like the opposite of reverse, you know, kind of what happened. Oh no, it's like what happened here. The reason why I went from here to here and here, make sure I explain it. Like the step 5v squared, the 5 divides u squared. It's because u squared is equal to 5 times the number. We don't care what number it is, but it's 5 times the number. That means you can divide by 5. Same thing here. 5 times the number equals v squared. That means v squared is divisible by 5. Then, like before I explained, it means that v is 5. Point is, you get u divided by 5, and 5 divides u and 5 divides v, which is a contradiction. Because this would mean, because GCD of uv is supposed to be 1. But this contradiction implies that square root of 5 is not in Q. No, therefore it has to be irrational. But the whole issue here is this. You can understand, because basically this would mean the GCD, since they're both divisible by a number, it means that would be a divisor, a common divisor. And if 1 is the greatest common divisor, you can't have any number greater than that definition, and basically that means that 1 is, 1 is the only number they share that they can divide by. So any number other than 1. And 5 is definitely larger than 1. You can think of it like that. One more problem. Explain why this statement is true. If n is an odd integer, GCD of n plus 2 equals 1. Very quick in order. You just have to be able to look back on the theorem. If a equals qb plus c, then GCD of ab equals GCD of bc. It's a direct scene of that. Direct use. So, if n is an odd integer, GCD of n plus 2 equals 1. You want to prove this true. Right here. A equals qb plus c. We have n plus 2 is a. Q is 1, b is n, and 2 is c. So if that is the case, we have this as the case, then GCD of AB equals GCD of BC. So n plus 2 and n are A and B. GCD of n and 2 are B and C. GCD of BC. Very quite simplistic, I think. The setup at least. Then just n equals odd implies that n equals 1 plus 2 times x, and z. That's the general formula for an odd number versus an even number. Even is 2 times x. Odd is 1 plus an even number, basically, which even is 2 times something. So yeah, GCD of n and 2 equals GCD of 1 plus 2x, 2. Basically a statement now with that in mind. And instead of positive divisors, 1 plus 2x is a equals 1, 3, 5, so on for infinite amount of times. Eventually get to 1 plus 2x. Just say, instead of positive divisors of 2 is 1 and 2. So intersection of the sets A and B is 1, largest common divisors equals 1. So basically, yep, and that proves the point. If n is an odd integer, of course. And that concludes this.